less, but your mileage may vary. So why is this? Again, I don't want to dig too deep into the media details for why this is with SSDs, but I think it is worth mentioning briefly the background of like where this phenomenon comes from. And fundamentally, it comes from the fact that for NAND SSDs at least, you can only write pre-erased pages. So these are typically 4K IOs, 4K pages on the media side. These are very, very fast. You can write them very, very quickly when they're pre-erased, but you can never overwrite them. When you need to erase them, you have to erase full erase blocks. These are much, much larger, and you're going to erase a lot of pages. So this operation is very, very slow and hurts performance. So like I say, a couple quick examples of this, because I think we're all kind of up to speed on how SSDs work. They're not exactly a new technology. But write amplification is an effect you're going to have for SSDs. So here's a really simple example. Here we've got 3 erase blocks, basically. And we've got a new write come in. So those are the green blocks. Write it all very, very fast. But if you want to overwrite it, you just can't overwrite that one sector. What you're going to have to do is read all the previous data likely and write it to a new unwritten spot, because you can't overwrite in place. So this can lead to a very simple version of write inflation on the SSDs. So here we only needed to write 1 page, but effectively we wrote 4 instead. Not great. This can obviously get much worse. Along with this, another effect people know about for SSDs is garbage collection. So here we've got the same blocks, the same 3 erase blocks, and now we've got old data here on the middle one. This is data that the SSD moved internally. It knows it's not valid anymore. It knows where the real good data is. But we can't write those blocks still. So if you've got another write come in, you're going to need to erase that. Erasing that block, really, really, really slow with SSDs. So you come in, you do an erase, you write the new data there. This full erase write cycle is really expensive. So that's just a quick issue of the problem with SSDs and why trim's important. So the solution to this needs to be tackled at the file system level. And this is why people are keen on having trim in their file systems, because only the file system knows which blocks are actually allocated and which blocks are actually free. The SSD internally can be very, very clever about making sure things get pre-erased and moving stuff around, but at the end of the day, it can only do so much. And this gets a little bit harder too, the fuller the SSD gets. Right? The more data it has that it has to manage internally, the worse this problem gets. And it manifests itself as reduced write performance over time with your SSD. So, again, originally file systems were optimized for hard drives, so this wasn't a problem. Unlike SSDs, hard drives don't suffer this rewrite penalty. You can pretty much expect the same rewrite performance, more or less, for your drive, for the life of the drive. For SSDs, trim's kind of more of a requirement, right? Because you expect the performance degradation. And internally, like I say, the drive can only do so much. So there's some nice effects that come from this and motivations for implementing trim support in ZFS. Again, that's probably why it's been one of the most requested features. It's going to reduce write amplification because of it's going to reduce write amplification. Basically fewer writes, because we're not going to have this problem as much internally where we need to move things around in the SSD. You're going to get higher write throughput, typically if you have pre-trimmed devices, because you've got a lot of these pre-erased cells that you can write to very quickly. And additionally, it's going to improve device longevity, because if you're not doing these, if you can minimize erase write cycles on your media, so much the better, right? Because all of these flash devices have a limited lifespan. So what you've seen is that trim support has systematically been added to most Linux file systems at this point. This is true for most other platforms as well. ext4 added trim, ButterFS added trim, even FAT, ZFS, and XFS have all added trim support at this point on Linux. But the story doesn't stop there. It's actually a little bit trickier than that, because a file system can have trim support and still not behave particularly well. So it's for this reason that it's disabled by default in a lot of Linux distros for just out of the box. Like you make a new ext4 file system on some distributions, trim just isn't enabled because it doesn't necessarily there can be performance concerns with certain devices, right, where performance isn't great. So it's something you gotta be a little bit careful with. So you may have noticed I missed one file system before. So ZFS. ZFS has actually had trim support for a long time now, right? Going all the way back to FreeBSD 9.2, there's been a version of trim in ZFS. Nexenta added a version 2 to their product. So trim support, we've noticed, been a good thing for a long time. And there's been versions of it out there, but none of those made it into the Linux port. That was until the last release. And the last release, at least for ZFS on Linux, 08, we went and took it as an opportunity to revisit why trim support had never been added, and to look at how we really wanted to do it in the port. So, design goals. The first one, probably a no-brainer, right? We want online trim support to not hurt applications. It should actually help application performance. We don't want it to negatively impact anything. Additionally, we want it to interoperate seamlessly with all of the existing OpenZFS features. This is one of the things that held back getting trim support into the Linux port for quite a long time, is you may have noticed that there's been new features added to ZFS at a pretty steady clip. And one of the things we pride ourselves on is having all of those features work really well together. So porting one of the previous versions of trim was easier said than done, right? Because it needed to not only, you couldn't pick up the old code exactly as it is and add it in. You'd have to adapt it to work with all the new functionality that was in ZFS. So we wanted to make sure whatever was done here worked cleanly with everything. We wanted to avoid introducing any duplicate functionality for ZFS. Again, it would have been really easy to take one of the previous implementations, add it in, but that could result in a lot of additional code, because while the FreeBSD and Nexenta trim implementations are good and solid and work great, they were just written before a lot of these other subsystems were added to ZFS, and now we can properly take advantage of them. And we want it to be long-term maintainable. This again goes to like not adding a lot of additional code and keeping the design easy to reason about and relatively straightforward. We didn't want it to be overly complex. And because we wanted this to be used everywhere, I think it was important to keep an eye towards portability between platforms. And for trim in particular, this is a little bit bigger of an issue and something I'll touch on later. But we wanted the final implementation to be pretty portable. So these are all good things to strive for, but why didn't it happen until now? And the reason it happened now, and it was much easier, is because of a recent OpenZFS feature that got added. So in the 08 release, VDEV initialize got added as a feature, also known as eager 0. Anybody here familiar with VDEV initialize? They use it? Oh, good. This is the right crowd. Yeah, so VDEV initialize added as a feature to initialize unallocated space in the pool, basically as a background task for performance concerns. It turns out that on some systems, you may have a first access penalty. When you do your first write, if it's like a thinly provisioned device in a virtual environment, it may cost you a fair bit to perform that first write. And if you can hide that first access penalty, that's great. So that's what VDEV initialize is there for. In the background, it writes a pattern, zeros, to all the unallocated space in the pool. When you think about it, this behavior is exactly what you want for trim, right? This is exactly what you want to do with trim. You want to, in the background, not issue zeros to all the unallocated space, but you want to issue trim IOs to all the unallocated space. So building on VDEV initialize, like, put in place a large number of the components we already needed to implement trim, and we could do it in a way that leveraged all of that existing functionality, which was really nice. So in particular, I'm going to talk about all these components in a little bit, but just to touch on them briefly, VDEV initialize added a really nice CLI options for it, along with good reporting. The ability to enable and disable metaslab allocations. This is so we can safely initialize in the background this unallocated space. It added some infrastructure for us to figure out where to submit the IOs to the physical disks for the unallocated space. But everything we need wasn't quite there, right? Some new work was required. Originally, VDEV initialize was written just for that sole purpose, so it needs to be extended a little bit and made more generic. Additionally, ZFS has never had the notion of being able to issue trim IOs as a higher level concept. So it needed to be added to the pipeline to be able to do that. And automatic background trimming is another thing that needed to be worked on, and I will touch on that closer to the end. So, what got added? Manual trim. So there's a zpool trim command in the latest release. It does exactly what you think it should. It initializes an on-demand trim, and it trims all unallocated space in the pool. So the command line syntax is very much like VDEV initialize. Just give it zpool trim, give it the pool name. Additionally, if you want to restrict it to particular VDEVs, you can do that. Just specify the ones you want. There are a handful of options it takes. If you want to rate limit it, you can give it a -R. If you want to do a secure trim and your devices support it, you can do that. But its purpose is basically to go through and efficiently issue trim IOs for all of that unallocated space in the pool. That includes merging these ranges. Paul set me up great earlier today talking about range trees and metaslabs. So that's great. But the range trees basically handle all of the merging for ZFS trim. Right? We just walk that space. Furthermore, a manual trim needs to skip very small ranges when issuing trim IOs to disk. If you look back to the SSD stuff I mentioned, right, there may be no point in issuing really small trim IOs for the SSD if they're smaller than an erasure page, because the drive can't really do anything with that. They also may be slow, so these are things that can often be skipped. On the flip side of that, a manual trim needs to break up really large trim operations. What you don't want to do is issue like a 2 terabyte trim to device, right? Because it may accept it and then go out to lunch for a very long amount of time. Not great for user experience. Additionally, a manual trim, you can cancel it, you can suspend it, you can resume it. This is because we preserve the state for it on disk. So if your pool crashes, whatever, you export, re-import, we can continue on. So it behaves administratively from a user perspective in a very nice way. And all of this has been nicely integrated with the existing zpool status utility, so you can get good reporting for what's going on. So that was a lot of what it can do, but what does it actually look like? So zpool status looks like this now in the upcoming release, or not the upcoming release, but the current release. If you issue a zpool trim and you run zpool status, you'll see it broken down by individual VDEVs, which ones are trimming. And there'll be this little trimming line appended after them if they're currently in the process of a manual trim. Digging a little deeper, you can give it the -T option if you want to know a little bit more about the active running trim. In this case, it looks like the RAID Z devices here are about 2/3 of the way through, and they're currently running. It'll show you the percentage complete. The devices in the mirror, I've actually gone out of my way and suspended here. So what you can do is run zpool suspend and list particular VDEVs, and it'll suspend the progress for them. So they won't advance until you resume them. So if there's a performance concern or you're have some other issue where you want to pause them, you could do that. And then the last one here is done, right? The log device was smaller, really quick to trim the whole thing. It's complete. So you can always run zpool status -T and integrate it with the existing tools, get a good idea of what's going on with a manual trim. So that was a lot of high-level stuff, but let's go dig down into the internals here a little bit. And I'm going to talk a little about each of those pieces that I mentioned. So metaslabs. Again, we know a lot about metaslabs now, which is great, so I don't need to go over much of that background. But what we're interested in the metaslabs here is one range tree in particular for manual trims. There's a range tree in each metaslab called MS allocatable, and it's what's used to track the allocated space on disk. Right? So this describes all the free space and what we're going to need to trim from this particular metaslab. Building on the work that was done for VDEV initialize, we added the concept of being able to enable and disable one of these metaslabs. So when you disable a metaslab, it doesn't mean it's completely inaccessible. What it means is it's unavailable for new allocations, basically. So this is the fundamental mechanism that was added to allow us to safely trim the metaslab. You can now disable a metaslab and guarantee that at no time a new write is going to land on it. And everything described by that MS allocatable tree is safe to trim. It's okay if you read from the metaslab. It's even okay if you free blocks back to the metaslab. What you don't ever want to do is have someone write a new block to that metaslab, have it land on disk, and then accidentally trim it. And that's what this prevents. Again, we don't want to have too many of these loaded concurrently because they take a lot of memory. There's performance concerns with that. So what we want to limit is the number of metaslabs we can have disabled concurrently to some relatively small number. So there's controls that were added to the metaslab for that. And furthermore, they're ref counted. So like multiple threads can have the same metaslab disabled at the same time, so they can be safely operating on the same metaslabs. But fundamentally, metaslab enable and disable are the mechanisms we use to make sure we can safely trim all the blocks covered by a metaslab. VDEV translate. VDEV translate is the next important bit of the puzzle here. So with the MS allocatable range tree, we know which logical ranges we need to trim from disk. But it's a little trickier to map those to like physical offsets on disk. And that's what we get out of VDEV translate. So VDEV translate was like a helper that was added to the VDEV op structure that lets you do this logical to physical translation. So you can call the VDEV translate function and specify a particular leaf VDEV and a logical range you're interested in, and it will return the physical ranges on that VDEV. And those are what you can trim. So the strategy for this is pretty straightforward. Excuse me. So starting at the child, you walk up to the parent, basically, and once you find your parent, you initialize the logical range, and then you walk back unwinding the calls to the child, and there's a callback function registered at each of these levels that you can use to do this mapping. So by default, there's only two, right? There's one that's for mirrors and singletons, which is pretty straightforward. There's not a lot of complicated mapping that needs to be done there. But for RAID Z, there's a custom one, which helps you figure out like which part of that logical range exists on your particular leaf VDEV. And then when it unwinds all the way down to the child, it returns that range. So this provides you a way to basically say which part of this logical range exists on my child VDEV and what are the physical offsets for it. So that provides the second bit of this, right? Now we know what we should trim, and we know where it is on which leaf VDEVs. The last bit, and this is the bit that was added for trim. The previous two parts were added as part of VDEV initialize, because like I say, it's got the same problem, basically. But we needed the ability to issue trims, and this is where things diverge a little bit from the other ports. One thing that kind of bubbled up as interesting when looking at the FreeBSD and Exenta version is, and I didn't realize this at all until I started looking at them, but the implementations at the system level for trim are very, very platform specific. How FreeBSD handles a trim is very different than how Illumos handles a trim, which is very different how Linux handles a trim. The interfaces to do that are pretty different. And what we really wanted to do was prevent that kind of platform-specific detail from bubbling up into the core ZFS code, which it had in the other implementations, and it was awkward. Things just weren't quite in the right place. So what we did here in this version is made trim a first-class citizen for the I/O pipeline, basically. So now you can issue not just ZIO reads or ZIO writes. You can issue ZIO trims. And they're handled like reads or writes, like anything else in the pipeline. They aggregated properly. They get added to the queues properly for issuing to the devices. They're normal, full trim, or full I/O operations. So this made it easier to implement the platform-specific bits down at the lower platform-specific layer. Because now for like a block device, at least on Linux, you have a VDEV disk IO start function, and it's called with the IO type, and you get a ZIO, and it says type trim, and you just map that to the appropriate thing for your platform. On Linux, that happens to be the block dev issue discard function. You just pass in the range you want to trim, and it takes care of the details, regardless if it's on an ATA disk or a SCSI disk or whatever. It just hands it off the block layer and deals with it. But this way, each platform can do their right thing to handle trim for their system. Like I say, I was surprised at how different that was. VDEV file, again, you just implement the right thing for there. On Linux, VOP space is actually a wrapper for fallocate. So if you're familiar with hole punching on Linux, this really boils down to a hole punch. So if you have a file, it makes it into a sparse file. It punches a hole for that range. If your file system supports it, NFS, XFS, ZFS, all these things support hole punching on Linux. So you even get trim for files, which is nice. And most importantly, all the higher core components of ZFS don't know anything about this. All they know is that they're issuing a trim, right, for a particular space that range that isn't allocated. So putting that all together, this is what it looks like from an architecture standpoint. So when you issue a zpool trim, we're going to spawn one thread per leaf VDEV. So these are the orange boxes here at the bottom. These threads are relatively short-lived, and they're going to make one single pass over the metaslabs. And the idea is they're going to go through each metaslab and disable metaslab allocations. So we know that it's safe to trim that metaslab allocation. No new writes are going to be coming in. And then we're going to issue trim IOs for the leaf in question using the VDEV translate functionality. All right, we're going to say our leaf, and we're going to say, here's our top level metaslab, and we're going to trim it. Issue all of those trim IOs. It's a little more complicated than this in practice because there is you don't necessarily want to dump all of the ranges that would need to be trimmed on the device immediately. So there is some logic in there to rate limit things and make sure only so many trims are outstanding at any given time. But you issue them all and you wait for them to complete. When it's completed, enable metaslab allocations, and that metaslab has been trimmed, right? So repeat, go to the next metaslab, repeat the process. This is at a high level what happens with the manual trim. While it's going along doing this, progress gets saved in a leaf zap. So each one of these leaf VDEVs has a zap and stores the state in it. This is what's used for resuming if you suspend it, or progress reporting so it knows how far along it is. But the state gets tracked on a per leaf basis. Then you can cancel, suspend, resume. So what does this look like in practice? Here's what we expect. We expect performance to be good again for our SSD, and we expect it to drop off. But when you issue a trim, we trim all that free space, and performance should be returned on the system, right? We should have trimmed the device, performance should be good, but it will drop off again. This is where a lot of file systems kind of stop, and they say, well, this is good, just, I don't know, every day, every week, put in a cron job, trim your file system or whatever, and you'll have pretty good performance. But you still end up with the sawtooth behavior depending on the activity of your file system and how busy it is. So it's good, it solves the problem to have this kind of manual trim that you can do, but it's not quite what you really want. What you really want is an automatic trim, right? That runs continuously in the background and trims all the free blocks and always maintains good performance. This way, the underlying storage always has an update mapping of what the file system thinks is in use and isn't in use, and it can much more efficiently manage that storage to deliver good performance. This was added to ZFS via the auto trim property. There's a property you can set on the zpool. Set auto trim on or off. When it's on, you're doing automatic background trimming. So to make this work, there's one more piece of the puzzle, and that's the free block life cycle in ZFS. So when you have a block and it's really a free block, you're really about to free it, and it's not referenced by a snapshot anymore, or it's really going to be free. The block gets added to the MS freeing tree. This is a tree that's also attached to each metaslab. It'll migrate as transaction groups get synced, right? And this block actually gets freed to these trees called MS defer trees. It'll hang out there for a while, right, before we return it to the MS allocatable range tree. Once it's on the MS allocatable range tree, again, it can be allocated again by metaslab alloc DVA. Blocks, this is the normal cycle that blocks make it through on ZFS. So when you turn the auto trim property on, what happens is we get this other MS trim tree that gets added to the metaslab. Now, the MS trim tree is always going to be a subset of MS allocatable because it's going to contain only recently freed blocks on the system. So it'll be some subset of MS allocatable, and it also will only exist in core. It's never persisted to disk. So if you crash, you will lose this tree, but it doesn't really matter that much because it's only recent frees. And it's only a few, right? You can always run a zpool manual trim again if you really want to trim this space, but in practice, not having it be persistent was a really nice simplification and made it perform just as well. But when this trim tree is enabled, what you also need to do when you allocate a block in ZFS is you got to make sure that you also remove it from the trim tree, not just the MS allocatable tree, but the MS trim tree. And it's this trim tree that gets consumed by the VDEV auto trim threads for the background trim. So this looks familiar. Automatic trimming. This is the same diagram, but it's a little bit different for auto trim. So in this case, when you turn on the auto trim, you're going to get one thread per top level VDEV instead of one per leaf. It's also going to be a long running thread instead of a short running thread. In fact, it'll run as long as the property is enabled, just looping in the background. There are a couple advantages of having one thread instead of one per VDEV in this case. The big one is probably that it makes it easier to only disable one metaslab at a time when you're trimming it, because we don't really want to disable more metaslabs than we have to and disable allocations from more places. We want to have minimum impact on the applications. So if we can only disable one metaslab while we're trimming it and work on all of those children, that's ideal. Also, one thread is really more than enough to issue the IOs for the child VDEVs here. So we have one thread for that. It works very similarly to the manual trim process, except we're going to continuously iterate over the metaslabs in this case. So it'll start at the beginning. It'll disable one of the metaslabs, start at the top, I guess. And then it's going to consume that MS trim tree. And what I mean by swap here is when it consumes that MS trim tree, what it's going to do is remove it from the metaslab and insert an empty one in its place, basically. So this allows new frees that happen on the system to be added back to the MS trim tree, and we'll get to them on the next pass. It's not a big deal that they accumulate there for a while. It's fine. We're just gonna make it easier to operate on the current MS trim tree so we can traverse the whole thing and be done with it. We go through and we issue trim IOs to all of the children in this case, and then wait for them to complete. Like I said before, we're running at the top level of VDEV here, so we actually have to issue the IO to all of the children under us, whether they're a mirror or a RAID Z. And we use the translate function again to figure out where those offsets are, passing in the right children. Wait for the trim to complete, enable allocations, and we're good. That metaslab has been trimmed. The tricky bit with automatic trim, though, is that if you were to just do this, this thread would just spin in the background, right? Consuming all of your CPU, and that's not what you want, right? It'd be forcing transaction groups all the time. Every time you freed a block, it would cause activity. So the solution for that has been to group these metaslabs into metaslab groups, for lack of a better term. And by default, we group all the metaslabs into 32 different groups. And the idea is that at most, we're going to process one of these groups per transaction group. So that means it's going to take you a minimum of 32 transaction groups before you get back to trimming the same metaslab. That provides you 32 transaction groups worth of time to aggregate adjacent ranges together to issue them efficiently. We found that in practice, 32 works pretty well from testing. It's controllable. You can adjust it. But 32 works pretty well. Furthermore, the automatic trim is set up such that it never forces a transaction group sync. So the whole process is driven by normal transaction group syncs occurring on your system, but if you have pending frees in a transaction, they won't force the transaction group to sync because you really don't want it to, right? You want this process to be driven by writes. Just because there's frees, you don't want to necessarily deal with it. If your pool is idle this way, it stays idle if you're not actually doing IO to it. So you can't see this in the zpool status output, but you can see it in zpool iostat. So if you run zpool iostat-r while auto trimming is enabled, what you can see is additional columns on the right there. And there's an independent column which shows you the outstanding trim IOs. In this case, we've got, I don't know, some middle-sized ones in progress, but most of them are pretty large trim commands outstanding. So if you want to monitor it, that's an easy way to do it. This will be running all the time. zpool iostat-w. You can also get the request times for each of these trim IOs that are outstanding. And I don't know if I mentioned it before, but trim IOs are often very, very, very slow compared to normal reads and writes. And you can really see that in the graph here, right? Like the trim IOs are 100, maybe 1,000 times slower than a normal read or a write on this device. So it's important not to have too many of them in flight at any one time and to like manage them very, very carefully. But I thought it was interesting how they really like showed up in this graph or output. So what do we expect from auto trim? So we start a pool with auto trim off. We expect performance to degrade again, right? And then, we turn it on at some point, and then we expect performance to gradually improve as blocks are allocated and freed from the system, because eventually every block that we free is going to get trimmed on disk. So even if the pool was in a bad state beforehand and completely untrimmed, performance should gradually improve as we cycle through blocks and free more space. So we expect performance here to recover and be maintained. So what does this look like in practice, right? That was a lot of theory and a lot of hand waving about how we want it to work and why it's designed the way it is, but does it actually work that way? So here's the test case I ran, because I wanted to convince myself too, right? Does it actually work as it's intended? So the test case here is the time to copy the Linux kernel source. So what you want to test, what I wanted to test at least, to make sure the trim was working as advertised, was to compare performance of copying the Linux kernel, which is a couple of gigabytes and, I don't know, a couple tens of thousands of files at this point. How long does that take on a pool that has trimming enabled and one that doesn't have auto trimming enabled? And to do it at a constant pool capacity, right? Because we know, well, we mentioned before, there's this cliff past about 80%, which can totally skew your results. So at a target pool capacity of about 80%, how long does it take to copy this kernel? So the test case here is basically make 200 copies of the Linux kernel and then repeat this process, right? Pick one of those copies to remove it, and then time how long it takes to make a new copy in the place of that previous copy. So temp Linux here is just a RAM disk. So basically we're copying from a RAM disk into ZFS, timing how long it takes. The pool here also starts empty. So this RM might actually do nothing until we make our 200 copies. And 200 was picked just because for my particular pool that got me to 80% capacity. So details here. Rel, the hardware config, mirroring and RAID Z2 was tested. So what does this look like? So here's the data. Mirror and RAID Z are on here. What you can see is these are the averages over 5 runs, and then I've just got a little scatter plot there for each test point for each of the runs. So at the very beginning in a pre-trim pool, performance is good, right? We're making quite a few copies of the kernel per minute. It looks like about 6 copies per minute, something like that, which is what we'd expect. It's a completely empty pool. Performance is just fine. As we fill the pool, performance does degrade, right? It gets worse over time, and eventually it bottoms out somewhere. And this is all with, no auto trimming, nothing fancy, just enterprise grade SSD that we're testing with here. So that's the sustained performance down there at the bottom. To convince ourselves that really this is not because the pool's full, because you can imagine that maybe this is just a performance drop off to do filling the pool. We issue a Z-pool trim. Sure enough, you run a Z-pool trim, just like expected, performance pops back up. Almost back to where it was before, which is great. But also as expected, performance kind of goes down again pretty quick. It doesn't take too many more copies of the kernel before performance goes off a cliff. Z-pool trim again, just to convince ourselves that's really what's going on. Sure enough, it is, right? Then performance drops off. And then the really good bit here at the end is auto trim does work as intended. Once you set auto trim and you're freeing and allocating a ton of blocks, right? It actually doesn't take particularly long for performance to recover. And when it does recover, it's able to maintain that performance almost as if it were a new pool. So the good news here is all that theory actually works. Trim does work as advertised, and performance is pretty good. So that's all I've got. That's kind of a overview of how trim was implemented. And I guess I can take questions. Yeah. Doing like removing a data set and doing all those frees. Yeah, so I haven't run that exact test. I imagine that it would work pretty well because, I mean, they're all frees handled like any other frees. We rate limit how often we issue trims. So it might take a while to process all those frees as they aggregate, but it shouldn't affect the rate at which we're really issuing trims, as long as you're talking about the auto trim case. The auto trim case. Yes. Yeah. 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 Yeah, I've seen this. It's very sad. Yes, yes. Well, so yes, they will be broken up at the lower level. There's a threshold where I don't know what it is offhand, but we guarantee that we don't issue trims higher than, I want to say it's like 16 or maybe 32 megabytes, something like that. But yeah, there's a cutoff where we say, no, no, this is just a bad idea. Don't do it. Yeah. That's a good question. They can absolutely both be run at the same time. Um, oh, the question was, how do manual and automatic trims interact when they're run at the same time? So a manual trim and automatic trim can run at the same time. The manual trim basically runs as fast as possible, right? It's an administrative thing, and the intent is to trim all the free space in the pool as quickly as possible. So that will be run normally. In parallel, the auto trim will run, but I don't think it doesn't conflict with the manual trim, but I also don't think it necessarily factors it in. So you might end up pre-trimming the same blocks, but probably not a big deal. Yeah. Um, yeah, I'm sorry, I missed that. Why the question is, why do you need a separate MS trim tree for trimming? So the reason there is the MS allocatable tree describes all of the unallocated space on disk, right? We need a separate trim for MS trim because we only care about blocks that have been recently freed, not all of the blocks that are free currently in the pool. So you only want to trim things that were recently released. We could go through MS allocatable there, but that's a lot of extra work. And it's possible that a lot of those ranges have already been trimmed by a previous pass. Like if you had run a manual trim over the pool and trimmed everything in MS allocatable, then all that stuff is already trimmed. So like the previous question, if we had come through with an automatic trim and trim everything in MS allocatable or MS trim, which may overlap with that, it may just be wasted work, right? Those blocks may already be trimmed. So they're tracking two different things. Yeah. 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 So the question is, I mentioned that um, we don't force transaction group syncs. So when the pool is idle, we don't go do trimming in the background, basically. We wait for some new write to come in. The question is that not necessarily, isn't that a good time to do trimming, actually? Because the pool's otherwise idle. It seems like the perfect time to do trimming because it's not going to impact any kind of application workload. Um, yeah, from that perspective, it would be good because it wouldn't impact any application. But in practice, we found that even running when the application doesn't seem to impact performance much, and it's desirable for the pool to actually be able to quiesce when no one's using it. Um, you could imagine some kind of more complicated machinery, I suppose, where you go through and you trim everything once, and you drain all the trees, and then once everything's fully empty, you quiesce and stop. That could be left as future work. There might be value in that. Um, it didn't seem necessary in the first implementation, I would say. Yes. Yes, that's true. So the question was, yes, I was using fancy enterprise drives, and the story may be different for consumer drives. We did not extensively test consumer drives, so I could totally believe that you may need to tune this differently if you're using a low-end consumer drive. Um, Definitely, some work to do there, and someone should explore what the right tunings are. Yeah. Rate limiting for the trim. The question was what kind of rate limiting was done for the trim. I didn't mention it. The way the trim IOs are issued as part of those threads, they rate limit themselves basically. There's a control that controls how many outstanding trim bytes will be issued down to the pipeline. and then the pipeline itself does some limiting and breaking up of those IOs before they get submitted to disk. But yeah, I glossed over that. There was a buried in one of there. There's more detail about how those get broken up. Yeah. The impact on the read latency. I didn't run careful data on the read latency, so I do not know. I don't know. I don't know. I'd be hazard to guess on that. Like you say, it could vary widely between drives. From my personal experience, how SSDs behave does vary widely between the consumer grade, the enterprise grade, between the manufacturers, between a lot of different things. So I don't know exactly how it would behave there. Yeah. So I think the question was, what is the memory impact of maintaining this additional range tree, tracking the free, the ranges that are to be freed. It's pretty minimal in our experience, mainly because the tree itself doesn't get that big typically because we're pruning it fairly aggressively. Like every 32 transaction groups, you've basically drained the entire tree. It's also a range tree, which happily has been nicely optimized now, so that helps. And if you're in contiguous ranges, they don't take up that much space. So we haven't found it to be a problem in practice. I suppose it could be if you suddenly free a lot of stuff that happens to not be contiguous and makes really big range trees. It's not capped at the moment. Could be. I mean, if it turns out to be important, we could cap it. Yeah. This is in .8. Yes, the question was, is this in the current release? Yes. Can. Yeah, so the question is, what's the x-axis on this, right? I conveniently left it off, right? Yeah, so the x-axis here is test iterations, basically. So it's what each of these dots is one cycle of that remove copy loop. From beginning to end here, it's about 2,500 runs of the test, something like that, for perspective. So it probably took, when performance collapses here, maybe, I don't know, 30, 40, 50, maybe copies runs of the test before performance was back down below. That's going to vary based on how full your pool is. In this particular case, the pool was 80% full, so we weren't leaving ourselves like a lot of extra free space. So that'll contribute to it too. But the trim, so the trim time as an, yeah, I didn't mention. So pool must have been about 2 terabytes usable capacity, something like that. To get about 200 copies of Linux kernel in it. And how long did it take to trim? It's not reflected in the graph here because this is just iterations, not trim time. But the whole trim for a manual trim, I want to say was on the order of like maybe 2 or 3 minutes, something like that. Pretty quick. Yeah. So the question is, did I run the trim while the test was running, the manual trim, or did I run it in between? And the answer here is I did run it in between. So you're not seeing like the effect of a running manual trim and what it does to performance on the system. That's, yeah, the scripts just weren't set up that way. I'd be curious about that myself. I don't know what impact a manual trim would have. The auto trim was clearly designed not to impact things, but the manual trim is much more aggressive. Yeah, Stu. That's a good question. They were close enough that I didn't investigate that, right? I'm like, RAID Z, Mir, they're about the same, right? They're about what I'd expect. So no, I don't know exactly why it's a little bit slower. The question was, does VDEV translate need to take into account device removal? So the VDEV translate code pretty much just does that logical to physical mapping. And I forget offhand if the VDEV translate code. Do you know offhand? Yeah. Ah. Yeah. Yeah. So one other nice thing to add about that too is I meant to mention at the time, but because there's like a generic helper for this too, it's easy to extend the mechanism so it works with things like DRAID when it gets integrated, right? It'll be able to do that mapping and trim, and VDEV initialize will just more or less work with DRAID. Yeah. Uh-huh. Yes. Yeah. 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 That's right. Right. So to try and re-summarize what Matt just said, is it doesn't matter because the MS allocatable we're walking just represents like what blocks are allocated. It doesn't care what's in them. It's just what's allocated and what's freed, right? And we're just trimming all the stuff that's nothing is using, right? Yeah. We have not done testing at a large number of. So the question was, are we keeping a list of disks that we know are problematic, right? No, we try to just buy good disks for the most part. So we don't have a really long list of disks you should avoid. It'd be cool if someone had something like that, but no. Well, yeah, exactly. Like you've got a really bad disk and trim works poorly with it. Yeah, it could be bad. Uh-huh. Are they? Yeah. Hmm. Yeah. All right. So the question was, is there any additional delay between when a block is deleted and freed and when we actually go off and trim it? No, there isn't. So once it's added back to MS allocatable, we consider it eligible for trim. It might not mean we get to it immediately, depending on the thread when it revisits that metaslab to trim it. But yeah, it's immediately eligible. So there's not an additional deferred delay. So you can only, yeah, I'm about to say. Well, even, yeah, for automatic trim, you get the 2 TXGs too, because it does go through the MS deferred tree. So you get 2 transaction groups. So you can rewind your pool as far as you normally would be able to safely rewind your pool without having any risk of your data being gone. But once it was eligible to be overwritten by like a normal file system, right, it's also eligible to be trimmed, and it may be trimmed at any time. So no additional delay. Mm-hmm. Yeah. Yeah. So the point was that this does potentially eliminate or restrict your abilities to roll back because we're pretty aggressively trimming these things. That's absolutely true. If you don't want that, I would suggest not turning on automatic trimming, or we can, think about extending it if that's useful functionality you want to preserve and you want to delay it farther. I mean, that's the thing you could extend. Yeah. Yeah, exactly. Yeah. 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 I mean, I think that would all be worth interesting to explore generically, like as part of the MS defer tree. Like Alan was saying, right? Like maybe you want to let stuff last a lot longer. That's totally a reasonable thing to request. But I think it should apply uniformly to trim and like normal file system I/O, right? Yes. Yes. Mm-hmm. Block your Yeah. Yeah. I mean, that may still be the case in the Linux port, because just because it ends up on the MS defer tree, right? It may not be trim for another 32 transaction groups, right? It could be that long. Yeah. Ye- Well, if if the write's big enough, I think that's true, right? Like if you're doing a really big write, yeah, yeah, exactly, yeah, yeah. I think it would be really interesting, like we said, about checking out different SSDs. I bet they all behave a little bit differently. It's going to depend on the firmware, and we tried to tune what we thought would be reasonable defaults, right? Yeah. 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 So I guess the comment there was this may behave a little bit differently on SATA drives, which have different limitations, right? This was testing was done on SCSI drives, and hopefully they do a little better with trim, but your mileage may vary. Mm, yeah. um, it was pretty straightforward, I would say, but only because George paved the way for me to get this done, right? There was a lot of just extending that code, right? And then adding the bits that were missing, which I think was really nice, actually. It's nice to see these two features come together. Um, there was some trouble chasing data corruption bugs for a while. That was a thing we cared a lot about, obviously. And it's one of the things that really kind of delayed this work for quite a while, is like, how do you convince yourself that this is working absolutely correctly and is never going to do anything wrong? Because if it does, it's bad, right? So there was a lot of runtime and testing and running down those kind of bugs to convince ourselves that it was absolutely solid. Mm. Yeah. Mhm. Mm. So the question is, if you're running a pool with all hard drives that don't support trim, what happens with the properties? So at the moment, nothing. Basically, the properties are still there. You can turn them on, but each drive is individually detected whether it supports trim IOs or not. And if the device doesn't support issuing trim, it's not supporting that device. It won't issue trims to that device. If it does, it'll issue trims, and it'll report which ones which don't support it. So it just disables itself if the drive doesn't support it, and that's all detected for you. You don't have to configure that or anything. Um, yeah. Yes. So I didn't mention it, but this does not require a feature flag. So there's no on-disk compatible change. That was the other nice thing about not making the MS trim tree persistent on disk, is it required no change to the on-disk format. So nothing changes. Yeah. Yes. The question was, does the auto trim code disable metaslab allocations when it's trimming? Yes. Yes. That's the only reason it's safe. Yeah. I think it's, if I remember, it's based on the number of bytes outstanding. not the number of ops. Yes. Yeah, it's throttled at 2 levels. At one layer, for the manual trim, it's throttled based on a number of bytes outstanding we issue to the lower I/O layers in ZFS, the ZIO pipeline, and then the ZIO pipeline itself will determine when to issue those IOs based on other activity on the system. Like I said, trim was added as a full class member for IO types in ZFS, so it'll trade off between outstanding reads and outstanding writes and trim. And trim is like the lowest priority thing. So if there are outstanding, I think scrub might be below trim, but it's below reads and writes. So if there are outstanding reads or writes that need to be handled, they'll be handled first. Yes, it's possible, but the question was like, how's the throttle work? And the throttle works based on bytes at the higher level. So we're going to issue a range to trim, a certain number of bytes to the lower layers. And then the pipeline will issue IOs to handle those trims as it deems appropriate, as it's been tuned, right, to avoid impacting performance. So if there's a lot of reads that need to be handled, synchronous reads, the trims will be deferred in the queue and they won't be issued. Yeah. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Yes. So we should probably talk offline and hash it out. But yes. Yes. Sure. Mm-hmm. The question was why have an automatic and a manual trim? The thought process was because a manual trim and an auto trim are kind of serve different purposes. The manual trim, you really want to, as quickly as possible, return a device to a fully trimmed state, and that's what it does. It runs through the entire pool and trims everything that could be trimmable. It may impact performance, but it will get you to that fully trimmed state as quickly as possible. Like we said, it may just be a few minutes to get there. The auto trim is more for maintaining performance on a pool and keeping things in a fully trimmed state. So there's slightly different use cases. I guess you could make an argument that the auto trim gets you most of what you need, and you could just leave that enabled. But at that point, it's easy enough to have the manual trim too, and it's useful. Last one. Mm-hmm. Yes. Yes. So the question was, if you're allocating from a metaslab and we disable it because we need to trim it, then yes, your allocations are going to shift to other metaslabs, and we may have to load new ones because of that. But we probably have a couple of metaslabs loaded, so as long as we don't disable too many of them, which is what happens with the auto trim, right? It shouldn't be too much of an impact. The question was, do you have to take the lock to disable the metaslab? And yes, I believe that's the case. Yes. Sure. Right. Right. Seven. So Matt says there are normally 7 allocated. So disabling one is, you know. If we, yes. If we don't allocate. Yes. Yes. So we should be okay as long as we don't disable all of them, which is why there's the manual trim only allows a small number to be disabled by default. It's like 3 or something like that. Yeah. Yep. Cool. Thanks.